Hello and welcome. I'm Lee Harrison from Siemens EDA. Welcome to this Semi-Israel Tech webinar. Today we're going to talk a little bit about how to meet the challenges of ISO26262 for automotive IC design using our Tessent test solutions. So in this session, I'm going to cover a number of different topics. Firstly, I'm going to go through some of the ISO26262 basics, explain some of the requirements that you need to achieve to make sure that your device is able to be ISO26262 certified. I'm going to talk about how to use our test solutions as a safety mechanism, talk a little bit about data monitoring, and then give you a little bit of insight into what's next and how to find the resources to get started. Okay, so let's start with some of those ISO 26262 basics. Why do we have ISO 26262? What is it? And why do we need to be mindful of it? So ISO 26262 is a standard which prescribes the safety requirements that need to be addressed in any automotive component, whether that's hardware, software, and in our instance, the ICs that go into the vehicles themselves. And one of the real key reasons for having standards like this is because with the onslaught of technology within your vehicle today, none of us really want to have a system which is taking over the driving functions of our vehicle, either the advanced ADAS systems or maybe in the future the full autonomous driving functions, without them being 100% safe. So ISO 26262 really prescribes what's required from a safety perspective, and how we should address that and how we measure the safety of the various systems within our vehicle. So, so from an IC perspective, what does that really mean? So ISO 26262 covers two real scenarios. One is what we call our systematic faults. So is the device designed correctly? Is it constructed correctly? Is it verified correctly? So making sure that there is a process that anybody designing and developing automotive ICs works through to ensure that the outcome of the device is a safe, fully functioning, fully working piece of silicon. Then we have resistance to random faults. And this is where we'll spend most of the time today. And that is, once you have your fully functioning, correct and safe IC that's installed in your vehicle, what happens if that device develops a fault? So whether that's a physical fault that just appears through the aging or degradation of the silicon, whether that's a fault caused by any other environmental issues within the vehicle, or even if it's just a what we call a transient fault where kind of stray radiation particles pass through the device and have the potential to flip bits and digits within the device, which could cause the device to malfunction. And what we really look at here is the susceptibility to those random faults. So if a random fault occurs within your device, do we have a way of monitoring that? Do we have a way of flagging that an error has occurred? Do we have a way of detecting that there is a fault? Because the worst case scenario is a fault occurs, we're not aware of that fault occurring, and the result is vehicle failure and potential injury or death. So we need to make sure that the potential of any kind of defects is easily detected. There are a couple other standards which are kind of wrapped up in the same type of situation. So we have ISO 21448, which is otherwise known as SOTIV. This is really defining whether what you have created is fit for purpose, whether it's fit for the environment that it's intended to be used in. So, for example, the good example here is in terms of operating environments, a vehicle that's designed to be operated in a city, um, will it still work? Will the ADAS system still work in, for example, the Antarctic or somewhere like that? Is that really the environment that it's intended to be used in? So we've got to look at those type of aspects as well. And SOTIV defines how to bound that process. And then we have cybersecurity, ISO 21434. This really focuses on faults and errors that occur in the device and in the vehicle due to malicious attacks. So due to cyber attacks on the device, on the vehicle, that can cause the vehicle to malfunction or behave in a way that is not intended for the vehicle to do so. So that's all focused around the vulnerability to cyber attacks. But as I said, the rest of this session really focused on random faults. How do we detect them, and how do we mitigate against them? So in the standard, we have a number of statistics that we look at, and the key number here that we're really interested in is what we call the single point fault metric. Single point fault metric is essentially every potential fault that could occur in the device itself, and our ability to be able to detect that. You'll see here, I've just highlighted 3 different levels: ASIL B, ASIL C, and ASIL D. This really refers to the safety level that we're trying to achieve with this particular device or system. ASIL B being the easiest to achieve. So ASIL B is typically for infotainment systems, things that don't have direct control over the vehicle's key driving operations, so braking and steering. And then we go right the way up to ASIL level D, which is really the safety critical application. So anything that could cause the vehicle to brake as not expected, steer as not expected, and anything that is potentially going to cause significant injury or death if it malfunctions. A couple of other numbers there. The latent fault metric is really referring to when we see potentially 2 defects that are kind of aligned, so that if an example here is if we have a single point fault failure in the functional logic, and then we also have a single point a fault in the safety mechanism which is detecting those faults, which essentially masks that detection, then we refer to that as a latent fault. You'll see that the coverage requirements for these is lower, and this is essentially because the potential of 2 faults occurring that could potentially mask the effects of one another are very much reduced in possibility. So actually the requirement for your latent fault metric is significantly lower. Another key metric that is talked about in the ISO standard is what we call our FTTI, which is our fault tolerant time interval. This is really important because this is the time that's prescribed between when a fault is essentially detected or a fault occurs in the device, and the time it takes to detect that. So we're really interested in this particular time here, which is the diagnostics time interval. And as I said, this is the time between the fault occurring and our ability to be able to detect that fault. So when you're using for example, test technology, say logic BIST, within your automotive IC. This will essentially be the test time of the logic BIST. So we need to be able to detect the fault that has occurred within this diagnostics time interval. And this becomes more and more of a challenge over time as the devices are getting bigger and more complex. It's becoming more and more difficult to achieve that diagnostics time interval within the prescribed requirement. The other parts of this graph show that once we've detected the fault, there's a reaction time, and for example, this is the time that the rest of the vehicle systems take to put the device and the vehicle itself into a safe state. So essentially, the flow here is that a fault occurs in the vehicle. It takes a set amount of time to detect it, which is the diagnostics time interval, and then it takes a certain amount of time to react to that fault and put everything in a safe state. So that is your complete fault tolerant time interval. And really the bit that we have control of and have focus on is the diagnostics time interval. So within Siemens Tessent group, what sort of technologies do we have that help you achieve those ISO26262 goals? So first of all, we have a whole range of structural test technologies. So looking at memories, logic, really trying to identify as many potential defects within the silicon as possible. We have other functional safety technologies, which again monitor key pieces of the design and look out for defects and anomalies as they occur. And then looking ahead and into the future, we're introducing new technology called embedded analytics. Embedded analytics is really taking things kind of up a level. So where with the other technologies, we're really looking at physical silicon defects. With the embedded analytics, we're looking more at the functional behavior of the device itself. So here we're looking at the performance of the device. We're looking at security aspects of the device. So maybe looking out for illegal transactions in the functionality, and just generally monitoring other safety aspects. So this covers a really broad range of different technologies that really focus on everything from real physical silicon defects right up to the functional operation, which could be impacted by software, security attacks, and all of those type of things. So we really do have a wide range of technology to help you. So now let's take a look at the test solutions that are available that can be used as a safety mechanism to help you build up that ISO26262 diagnostics coverage. So here is what I call a typical automotive IC. In here we've got a whole range of different functional technologies that is all wrapped up with the Tessent test and embedded analytic infrastructure. So in here you can see, let me just pull up a quick pointer. Here you can see we have a memory, and embedded in there to test those memories in system. From a safety perspective, we have our TMB, which is our Tessent memory BIST, and again we have the same technology here, and this is all hooked together with the test infrastructure, which is based around the IEEE 1687 IJ-tag standard. So all of our test instrumentation is connected hierarchically through the IJ-tag technology, just to make things easy from a communication perspective. We also have in here some of the other functional safety technologies. So you'll see we have some ECC also monitoring for defects occurring. We can add parity, we can add logic duplication, and these are all additional technologies that can help detect defects that occur in the device when it's in operation. I also included in here the embedded analytics infrastructure. So this is really a separate monitoring architecture that sits alongside the functional and the test infrastructure with the ability to be able to detect, as I said, those functional anomalies as they occur in the device. And then we have our manufacturing test. So here we've got EDT, our compressed ATPG engine, again hooked into IJTAG for that ease of control and setup. And then to manage and control everything within the device, we have our in-system test controller, which we call mission mode. Mission mode is essentially connected into the IJTAG network here. So mission mode is the in-system test controller, which like I say, can hook into the IJTAG network and completely internally and in system can set up, configure, and monitor all of this test infrastructure that we've inserted. And to drive that, we can add a safety island or a safety manager, which is a CPU running safety software code that enables us to be really flexible in how we control our mission mode controller and monitor all of the test content that's in the device. Just quickly, some of the test technologies that we can use as safety mechanisms. Logic BIST. Logic BIST is a BIST technology that's inserted into the device that's able to use the existing scan structure and able to test the logic structures within the device. We share parts of that IP with our manufacturing test compression technology. So what you get is a very optimized solution where you're able to run both manufacturing test and in-system test just changed by simple configuration. So the same technology and the same infrastructure is used both for manufacturing test and also the in-system test. If you look at the roadmap for the logic-based technology over the years, you can see it's been around for quite some time. We started to get quite automotive focused around 2016, where we introduced the in-system test controller. And then in more recent years, we introduced a technology called observation scan, which I'll talk a little bit more about in a second. And then more importantly, for those people doing automotive designs, we also took our in-system test IP completely through the ISO26262 certification process, right the way up to that highest level of certification, which is ASIL-D. So anybody picking up our test IP and using that within their automotive device can be rest assured that the IP itself that we generate for logic BIST and memory BIST and our in-system test controller are already ISO 26262 certified. And then most recently, we introduced a fully integrated flow with our manufacturing test SSN solution. So I think if you look back over previous SEMISRAL tech events, there was quite a nice presentation from a colleague of mine, Peter Orlando, who goes through the SSN technology. And now we have that fully integrated with the logic BIST and in-system test technology as well. Observation scan, which I mentioned before, Really, with observation scan, what we're trying to do is reduce the overall test time of logic BIST. We do that by leveraging the shift cycles that occur with every logic BIST pattern to achieve fault coverage on every single one of those cycles. Normally, those cycles are essentially just wasted cycles as the pattern is loaded. But with observation scan, we add these observation points, which enables us to accumulate coverage throughout the shifting of those test patterns. And again, that is really to target this diagnostics test interval. If we look at some of the results from observation scan, what you see here is we've got 10 designs that we have internally that we have run some experiments with. If you look at the baseline, with this is just regular logic BIST. For example, design one, we needed nearly 53,000 patterns to achieve a 90% coverage target. When we introduce observation scan, we're able to reduce that pattern count down to just over 3,000. So you can see this gives us a massive reduction in logic BIST runtime, which in turn, if you go back to the previous diagram, it shows a massive reduction in logic BIST overall runtime, which means from a safety perspective, not only you are able to achieve that 90% within the DTI time, it means that the device is a lot safer because you're able to detect defects a lot quicker, essentially. Just quickly on memory BIST, which I haven't spoken about too much, but memory BIST, another in-system test technology. One of the challenges here is typically BIST technologies are destructive. So if you're running memory BIST as part of your in-system test, it will destroy the contents of the memory in doing so. So we have what we call our non-destructive memory BIST controller. With this, we're able to test the memory whilst the device is in its functional mode. And essentially what we do is we take small pieces of the memory offline, one at a time, and we test those individually, putting the data back once we've tested it. So essentially we can test complete memories throughout the duration of the device being functional. Let's take a quick look now at the monitoring side of things. So I talked a little bit with the larger block diagram about safety island and managing all of the test content. Here we see our mission mode test controller in a safety island configuration. So any of those who are familiar with designing automotive ICs will have heard of the concept of safety island before. Safety island is really an area of the silicon where we keep all of the test and safety logic separate from the functional logic. So here you can see we've got the in-system test controller, we've got our safety manager CPU, and the only real interface to the rest of the device is through this IJTAG interface. And as I said before, the safety manager CPU enables us to manage all of the safety content with software, which means that we can be completely flexible about how we run our tests, when we run our tests, and essentially what we do with the results that come back. If we extend this concept still further, what we can do is combine using this safety island concept, not only the test technology, but also the embedded analytics technology, any functional safety IP, and any parametric monitors that you have in your device. So all of that different test content can be managed through the safety island, through software, with the ability to take that data off chip via external communicators, where the data can be collected in the cloud, for future analysis, and this is really useful when there is a whole fleet of vehicles. There's an immense amount of data that we can collect and analyze. So just quickly before we wrap up, let's take a look at what's next and what's coming down the line. So we talked a lot about in-system test using logic-based. Logic-based is a great technology, but it struggles to achieve extremely high manufacturing test quality. So looking to the future, we're looking to bring in-system deterministic patterns into an in-system architecture. So being able to run your manufacturing test patterns in a way that we can do that in system, and that will give you a lot higher quality and coverage, which we expect to be demanded of in the future. So how do I go about getting started? Well, as I said, we have two levels of ISO certification. So firstly, all of our Tessent test tools are certified to ASIL TCLs. So this is a tool readiness standard. And then all of our Tessent IP, so the memory-based, logic-based, and in-system test is also certified to ASIL level D. So in summary, ISO 26262 certification is required for all automotive ICs. The in-system BIS technologies provide the ideal solution to achieve this very high diagnostics coverage, which is required. The technology can also form part of an overall lifecycle management process. So really looking at the life cycle of the device. And then with all these technologies, there's repair mechanisms that can be implemented to repair either parts of memories or swap in logic cores as and when needed. And then just to reaffirm, the Tessent technologies, the software tools, and the IP have all been ISO 26262 certified. So today I've talked about ISO 26262. There is other parts of this story which I mentioned at the beginning, the ISO 21434, and what we're starting to find out is there's no real safety without security. So security is just as important as the safety part. Okay, thank you very much for your time and your attendance, and I look forward to talking to many of you in the future.